Greetings, fellow learners. In this video, we are going to visualize convolution and pooling layers in convolution networks. Now, what we have here is we're actually going to walk through 6 types of networks, starting with like feed-forward neural networks with no hidden units, and work our way with adding convolution and pooling layers and activation layers, and then try to visualize what's going on in the network, what is actually being learned, and also any variations that we can see for performance when we try to shift, rotate, or scale the input images. So it's going to be pretty fun, so let's get to it. Starting with network number 1. So we have a feed-forward neural network with no hidden units. So let's first walk through the model training and the architecture itself. So this network is going to be 28 cross 28 MNIST digit images. So that is going to be flattened and then piped into 10 output neurons with no hidden units. And when you train that network, you're going to get these visualizations over here. So the way I constructed this was that for each output neuron, let's say like the first output neuron, which represents class 0, it has 784 weights that are associated and tied to it that are coming from all of the pixels. So basically, I took all of the weights and then rearranged them into 28 cross 28 grid in order to get this image over here. Red indicates higher positive values, and then the blue indicates more inhibited or much lower values. So this could be like really negative, for example. And what we kind of see here is that this first neuron in the output layer is maximally excited, or the output is going to be maximum for its activation, if we get some kind of input that looks like this. So it kind of looks like a 0, as effectively. Then the next neuron, which is going to represent class 1, is going to be maximally excited if we have, a input that kind of looks like this. And you can kind of see 2, you can kind of see like this kind of looks like a 2 over here. For 3, this third neuron, it kind of looks like a 3. And 4, it kind of breaks up a little bit, but you can kind of see the resemblance for all the other digits moving forward here for 7, 8, and 9. So clearly this network is certainly learning something, and what it is learning is essentially some average of the training data samples itself. So this is kind of like the average of zeros that is kind of being learned, for example. So now that we kind of visualized the weights and what they are learning, let's try to understand its performance. So with the MNIST data set, we've trained on 60,000 handwritten digits, and then we are going to infer on 10,000 digits. And here is an example of an input sample. And when we pass this into our current model, we see that it predicts the number correctly with its output activations that I've listed out over here just for reference. And if you actually try to see, of these 10,000 cases, how many of them were correct? Well, it actually gets a 92% accuracy. So of 10,000 cases, it predicted 9,235 of them correctly. And the total number of trainable parameters here is 7,850. Makes sense because it's 28 times 28 for the input layer and then 10 for the output layer. So that's 7,840, plus you have like 10 extra bias weights too. So that's the performance here. But what happens if we actually take the input image and we start shifting it? Let's say we shift it by some 5 pixels to the left. So instead of passing this original image, we pass the exact same image 5 pixels to the left. And you notice here now the performance tanks. You see the prediction is incorrect as it predicted 0, 1, 2. It predicted, this activation kind of won out instead of 4, 5, 6, instead of this activation over here, which completely decreased. And when we actually see the overall performance, testing on like 10,000 image samples and shifting all of them by like 5 pixels, we get 16% as its performance. So completely tanked performance here. Now, let's see what happens when we rotate image samples. So we take, for example, our 7 and then rotate it by 30 degrees and then pass it into the network. Well, in this case, it's also an incorrect prediction. And if we try to, again, rotate by 30 degrees all of the 10,000 test cases, you're going to see that the performance is 55%. Better than translation, but still not great. Now let's try to look at zooming or scaling. So let's say that we take our input image and then we will zoom out by 0.5x. And here the prediction is also, again, incorrect. And we can also see that the performance overall for, these, take all 10,000 cases, scale it out by like 0.5. The performance is only 18%, so also pretty bad. Now, I'm going to log all of these. So this is kind of a summary of what we just saw of like performance, number of parameters, and performance when we distort the training or the testing outputs, keeping the training set the same, by the way. All right, so that was network 1. Now, let's talk about this second network and its model training and architecture. So this second network is very similar to the first. The only difference is that we now have a hidden layer of 64 units. So these 64 neurons now ideally should act as feature detectors, and we should detect some more complex features. We are also going to add a ReLU activation after this fully connected layer so we can get some nonlinearity into the network and thus make the model more expressive. And so it should be able to represent more complex data. So now we train the model. Next, we can try to visualize what's going on. And when we visualize, the way I'm visualizing it here is I'm actually just going to, let's say we have the input of like 784, right, pixels. This is going to be piped into 64 neurons, right? And what we're looking at now is each of those 64 neurons, like the first neuron, is going to be connected to 784 pixels. I've rearranged those pixel weights, the weights that are learned, into a 28 cross 28 grid, and then displayed it on the screen over here. So that would be neuron 0, whatever you see here. Once again, if it's more red, that means it's a higher weight. If it's a deep blue, that means it's a much lower weight, right? And if it's white, it's kind of like in the middle or average weight. So what we kind of see here for, we have like each of these will be like, there should be like 64 of these, but I have displayed, I think about 20 of them over here, right? And what we can kind of see is like these feature detectors, it's effectively what they have learned. So something that, I kind of notice here is like, if you look at like neuron 5, right? It kind of looks somewhat like a 2, this red region. So it is more maximally excited. This specific like neuron 5 is maximally excited if we see like this top hat of a 2 and also this this diagonal line of a 2. And similar to like neuron 4 too, you can kind of see there's like also this diagonal thing going on. Maybe it's a 7, maybe it's like a 2, right? And then for neuron 3, you can see that it looks kind of like, it'll be maximally excited if something like a 0 were to pop up here, in the input. So kind of keeping this in mind, I know it's a little bit tricky and somewhat, challenging to visualize, but, keeping this in mind, let's try to look at the next layer. So what I've done here is now, the next layer is the 64 neurons are connected to the 10 output neurons. And so what that means is like, for each output neuron, it's connected to 64 neurons, and I took all the weights effectively there, and I just made it into an 8 cross 8 grid. And that's exactly what represents this 8 cross 8 grid here, right? So effectively, it doesn't actually represent anything. It doesn't have to be organized in a grid like this. It's just specifically for compact, visualization. That's about it. But what we can kind of, see here is, well, let's try to look at, some of the cases that we mentioned before, right? So you see that for class 0, you see for neuron 0, 1, neuron number 2, it is quite red, right? Neuron 2 and neuron 3. So that means that, if neuron 2 or neuron 3 are excited, then that means class 0 will also be excited. That means its activation will increase, and the chances of predicting class 0 increase. So let's actually look at our image for neurons 2 and 3. We kind of mentioned this before, but if you kind of look at like neuron 2 over here, you see that, if you do pass in a 0, neuron 2 does get excited, and hence that class 0 neuron will also get excited. So you can kind of see how it's learned to represent a 0. And same with neuron 3 too, right? If you pass in a 0, neuron 3 gets more maximally excited, and so class 0 neuron will also become excited. Now, let's go back and just, look at another example just to solidify, our understanding here. What's really cool is this class 2, right? You can see if neurons 2, 3, 4, 5, and 6, like all of these, neurons 2 through 6, if they are excited, that means the neuron representing class 2 will also be excited, and hence the network will likely represent, class 2. It's going to predict class 2. So let's look at the features that were kind of learned by neurons 2 through 6. Well, you can kind of see like how they represent 2 a little bit, right? This is somewhat indicative of where we have a 2, right? That like a top hat of a 2. Same with this, it's like the top hat of the 2, and then you have like this part too, right? Similarly with neuron 4 especially. Neuron 4, it kind of looks like a 2. Neuron 5 also kind of looks like a 2. And if you squint, kind of neuron 6, but like you can see neurons 2 through 5 certainly look quite 2-like. And that is exactly what we are seeing right over here. And so you can kind of make your own, assumptions and try to like also see any correlations between the previous net weights and these weights too. And I hope it also becomes apparent of like how this can be used as like a great visualization tool for the network. All right, now that we kind of visualize what's going on, let's take a look at some base performance. So let's say that we have our same test input image 7, and when we pass it to this network, we see that it predicts the image correctly as 7. And the base performance is now 96%, so it jumped up from 92%. But the number of trainable parameters increased by, 7-fold. I think it was 7,800 before, and now it's 50,000 parameters. But what happens now if we just have the same, train set, but we just shift all the pixels of the test set by 5? Well, at least doing like a preliminary prediction for this 7, it seems to predict it correctly. And the test performance it's not great, but it is still much better. It's a 26% as opposed to like the 16% that it was before for the previous no hidden layer case. Now, when it comes to rotation, let's say we now rotate by 30 degrees. It still predicts a 7 correctly, which is great. And the performance here is, again, much higher than before. It's almost 70% compared to the previous case. Next, scaling. Well, when we scale the image, you can see that the prediction now, it's 1 instead of 7, which is incorrect. And scaling performance is still pretty bad. Maybe marginally better than before, but still quite bad. So if you were to compare these two together, they kind of look like this, where the current network is more performant in almost every way than the previous network with no hidden layers. But the total number of learnable parameters has also skyrocketed by 7-fold, which means that it's going to take a lot more time and cost to train this network. Although it's a small network, so it doesn't make too much of a difference here, but mentioning it just in case. All right, now that we looked at those two networks, let's now move on to visualizing an actual convolution network. So first, let's start with the model architecture and training. So this kind of architecture, it's going to have the 28 by 28 images are going to be input, and we are going to have kernels. We are going to have 8 kernels or filters. Each of those kernels is going to be 5 cross 5 with the stride 1. So when we perform a convolution operation of each of those kernels onto our main network, it's going to, transform the 28 cross 28 image to a 24 cross 24 image of sorts, or rather feature map is what we call it. Now, this feature map is then going to be flattened out. We have 8 of them, so we flatten all of them out and then pass it into like the 10 output neurons in order to get the prediction class. So that's our network. And note here, there is no activation function. It is just purely a convolution operation that we are then flattening out. So let's see the visualizations here. Well, when we just visualize the filters, that is the feature detectors alone, you can kind of see that each of these feature detectors or filters, it's really hard for us to really know what they really represent. Each of them is like this 5x5 grid. But, because it's so hard to kind of see what they've actually learned, it's easier for the convolution case where we take an image now and we're going to pass it into each of these filters. We're going to convolve it, rather, with each of these filters and then visualize the output of that, which is going to be that 24 plus 24 feature map. So let's do just that, right? We have an image. We've convolved it with the 8 learned filters above. And when we apply the convolution operation, we get these images over here, these feature maps. And what these feature maps, well, we can kind of try to interpret what they say, although it's not really easy to directly say what they have learned internally. So you can see that, again, the red regions indicate maximal excitement. The blue regions indicate maximal inhibition. So whatever's the really red and really blue regions, those are the pieces of information that are going to be passed to future layers, right? So in this case, like we can see that feature maps 0, 1, they're kind of like detecting edges, right? That's why it's like maximally excited here. And then you can see that like feature map 6 is like detecting the stroke of the 7, right? Feature map 3 is also kind of like detecting the edges, and it's also inhibited by like the stroke too. So overall, you can kind of like make these kinds of suppositions of like what each of these features represent, but it's pretty clear too here that they are they have detected in some way some part of the 7. And so you can kind of gauge that training has happened correctly, at least to a certain degree. We can also visualize kind of the same thing for like another input, like if it's 0, for example. You can see that feature maps 0 and 1, they are like detecting and going to like really highlight these edges, and they're probably also going to be inhibiting the stroke itself. Same with like feature map 4. And then feature map 6 will be maximally excited by, again, the stroke of what's going on in the image, right? So now that we've kind of visualized what like the feature maps look like and hence the effects of the filters, we can try to look at the performance on like the 10,000 MNIST data set. So when we have a 7 that's passed in here, now we have a prediction that's 7. So it predicts it correctly. And the performance here is 91.93%. So this is the lowest that we have seen so far, with the total number of trainable parameters also pretty high. It's almost as high as the previous case of like 50,000 parameters. And likely why we're seeing very poor performance, even, compared to like both the other cases, is because there is only linear transformations that are happening through the network. All the way from the image input to the output, there's only like sums of products that are calculated. So effectively linear transformations, and so the expressive power of the model is diminished. So you can see that the model could be potentially underfitting here. We're going to solve this in Network 4 by adding activations. But before we get there, let's try to see how this model did with shifting, rotation, and scaling. So when you shift all like the pixels by 5 pixels to the left, you get a prediction of 3, which is incorrect here. And the performance is 14%. Again, quite low. When you do rotation now, well, the 7 was predicted correctly. And rotation, it's still like 55% performance. Not great, but better than translation as we had seen in the past too. And then when we scale out by 0.5, we see the prediction is incorrect for an example. And when we test on like 10,000 examples, which are zoomed out, we see that's 18% performance. Again, not great. So almost entirely comparing like this current network to the previous network with just a hidden layer with no convolution, we see that the network currently now is underperforming in almost all accounts. And like we mentioned before, this is likely due to the minimal expressive capability of the current model, which we can increase now by adding an activation to the network. So let's say now for this fourth network case, we're doing exactly the same as we did for the previous network, but what we're doing extra now is that we're adding a ReLU activation here after the convolution. And then we are then piping this into a linear layer, which is then going to be, piped into like the 10 neurons to predict the digit that is input. So let's actually visualize what happened here. So let's say that now we have taken that original 7 and we pass it into our network. So when you pass it, we have like 8 filters now. These are the learned filters, right? If we pass it into each filter, the first row is going to be the output of the convolution operation. The second row is going to be the output of the ReLU activation operation. So what's happening here, like I said, if it's really red or really blue, that's like the maximal information that is going to be passed into the later layers of the network. And in this case, you could see like these really red positive regions, they're going to be, all the blue regions are going to be like completely wiped out here because of like the ReLU activation. It's anything that's going to be, if it's under 0, it is floored to 0, and only these positive pieces of information are passed through. So you can kind of see here, like, what is this like filter 1 detecting? It's detecting, this slash of the 7. Whereas, filter 0 and filter 7, they're filter 0 is detecting like the top stroke, right? Filter 7 is probably detecting like the edge of the top stroke. And then you have all of these other filters 2 through 6 that are kind of in some way still detecting some part of the 7 itself. And this information is going to be passed into the later layers of the network for making decisions. And, this is a good spot check just to see, okay, because it is recognizing like features that make sense of this 7 and that are indicative of this being a 7. And so you can say that the model, at least at this point, is trained in some sense correctly. Now, if we look at like another example, just to see what's going on here. So for this 2, you can kind of see here the top is the convolution, the bottom is the activation. And, this filter 1 is, for example, detecting like the edges of, the left edges of the 2, right? And then filter 4 looks like it's kind of detecting like the right side edges of the 2. And then filter 7, it's really detecting like this base of the 2 and the top hat as well. And then all of these other filters are kind of, detecting some parts of the 2 itself that is going to be passed into later layers of the network. So now that we visualize this, let's actually see the base performance on the original MNIST dataset. It predicts correctly just the, a sample input, right? Then it has a 97% accuracy on the test performance and no change to the training parameters. This is the best performance that we have seen so far, and this is quite indicative of the power of activation. Very simple operation, but very important for increasing the expressive power of our model. And we also see this reflected in, some of these stats over here too. So let's say that we perform, we shift all the pixels by 5. It's, the prediction remains the same, which is great. And when you evaluate on the entire shifted data set, it's 40% performance, which is not the best, but still much better than what we have seen before. Rotation too, if you do a 30-degree rotation on the data set, you'll also see it's like a 77% performance, more than we've seen before. And scaling, we'll see some similar results as well. Though it's pretty low, it is still greater than we have ever seen before. And you can kind of see here comparing like the current network with an activation and then the previous network without the activation, just to show like there is a big difference between the two, right? And the total number of learnable parameters has just remained the same. And so we can see the power of just adding a nonlinear activation in the model. All right, now let's go to network number 5, where we're going to now encounter pooling. So essentially, for this architecture, it's the exact same as the previous architecture, but after the activation, what we're going to do is add a 2x2 pooling operation here. So this is going to downsample our 24 x 24 grid, each of those 24 cross 24 grids into 12 cross 12 itself. So what we do is there's going to be like a convolution followed by activation followed by pooling. And because now we have like 8 of these like 12 cross 12 activation outputs, we're going to flatten them and pass them into our 10 neuron output to determine the digit. So we train this model, and now when we visualize, let's say we pass in this 7 again, this wonderful 7, and we visualize, what do we see? Well, we see here the first row is the output of applying the convolution operation. We have 8 of those filters, right? Then this second row is going to get rid of all the blue parts because it floors anything that's below 0. And so we end up with just, certain strokes of the 7 or shadows or edges of the 7 that are activations, outputs. And then you have a pooling operation, which is this last row over here, where pooling is effectively going to downsample this 24 by 24 into a 12 by 12. And it's going to summarize, it has the effect of summarizing pixels that surround each other, right? So we can kind of see here, what's passed into the later layers of the network is this stroke of a 7, or this stroke of a 7 here, or kind of this underlying top hat of the 7, or some other features that we're kind of looking at over here, right? And we can kind of see this too if you want to see it for like other test cases. You can just replace this with any number from 1 or 0 to 10,000, and you can see it in action for any test case. Now, looking at the baseline performance over here, for the 7, it looks like it predicted it correctly. And then overall, our performance increased even more to like 98%. But the number of trainable parameters, interestingly, went down by 4x. It was like 46,000, now it's 11,000. So by adding a pooling operation, we were effectively still able to increase the performance on our testing set, while completely like destroying the number of trainable parameters to 4 times less, making it less costly to train this model. Next, let's say what happens if we shift all of these all the images by like 5 pixels. Looks like, it's 37% performance. Not the best, but it's still kind of on par with the previous case. Now, if we rotate, we have 77% performance. And if we scale, we will have a 26% performance. So when comparing with the previous case, it's kind of similar in terms of stats, but the total number of learnable parameters has completely decreased. And so the model is now much cheaper to train. Let's now look at the last network here. And what we're doing here is we're just doing the exact same convolution, activation, and pooling as we did before, but we're going to stack another convolution, activation, and pooling afterwards. So we have this 12 cross 12 output from the previous case like we saw before. We're going to use then 16 kernels, each of case 5 cross 5, and we'll apply it to 8 of these 12 by 12 feature maps. And when we do so, each of these feature maps is going to go from 12 by 12 to 8 cross 8 because of the convolution of stride 1. And then we're going to do some pooling again to make that 8 cross 8 to a 4 cross 4, right? And then we're going to flatten all of the 16 4 cross 4 feature activations in order to get our final, 10 cross, the neurons for like 10 outputs. So what we do is we now have our model training, and when we visualize, what we'll see here now, if we go all the way here, is this is the block 1, right? Where we have 8 filters. When we apply convolution to the image, we'll get 8 of these feature maps. Then we can apply activation in order to get this, and then we can apply pooling in order to get this record over here. And you can see it's like a good summary of pixels in each case. These look like reasonable features. Now we go on to block 2, where there's 16 feature maps. So we take, like, for example, this right here, and we are now going to apply a 5 cross 5 convolution operation. Specifically, this is going to be a 12 by 12 cross. We have like 8 of these. And to this 12 cross 8 input, we are going to apply a 5 cross 5 cross 8 a feature, a filter, in order to convolve it across this entire thing in order to get a 8 by 8 output over here. And like this, we'll apply another 5 cross 5 cross 8 filter in order to get another 8 by 8 output activation. And we repeat this like 16 times. In this case, I'm showing you 8 of those outputs. So there's like 8 cross 8 outputs over here. In each case, for this case, we're going to apply activation, which is why you see no more blue regions, right? And then we apply pooling, which is what we see here. And then this is like filter. This is the activations like 0 through 7. And then here's the other activations from 8 through 15, right? So from 8 through 15, this is the result of the 8 cross 8s. And, this is the result of the convolution. Then we apply activation, and then we apply pooling over here. And so you could see these 8 and these 8 are effectively what is going to be passed to the later layers of the network. Now, as far as like understanding like what are these features actually learning, I'll say this, you might be able to kind of see what these features are learning from the first block over here. You can see there's kind of some semblance, some parts of the 7. You can say it's some edge of the 7, the stroke of the 7, something that we can say kind of, at least for these 8 feature maps in block 1. But when it comes to block 2, it becomes kind of difficult and abstract. I mean, you can kind of see that this is somewhat of a 7. You can kind of see that this is summarizing some like horizontal stroke. But honestly, in large part, it's very hard to tell exactly what this is summarizing because the feature that it is trying to extract is more high level and abstract, right? And this does make sense because when we look at even like classical cases like from the experiments of Hubel and Weissel, their hierarchical model suggested that maybe like simple cells detect edges, which are more simple to understand for us. But then we have like complex cells, which might detect some higher level features that are a little tricky to just put to pen and paper. And I hope that kind of makes sense as to like why some of these are abstract and why it could be a little bit difficult to understand like what's going on. But at least we can kind of visualize them here. And I did it for the same like for a 2. So if we wanted to visualize a 2, we can kind of look at the same feature maps activations here. Now, looking at performance here, let's say we have this 7, we now pass it into our network. We're going to get, it's a good prediction, right? And here now we get the performance that's the highest that we've ever seen with the number of parameters the lowest that we've ever seen, which is fantastic. So we're getting high performance with much cheaper training. But how does it fare to shifting, rotation, and scaling? Well, if you shift all of the images by 5 pixels, the performance is 50%, which is the best that we've ever seen. Then rotation, you can kind of see it's 81%. And then scaling, it's going to be 42%. So overall, still the best that we've ever seen. But let's actually kind of have all of these numbers in one place over here so that we can see like what's going on. Okay, so we have, each of the networks, some description that I just gave for them, their base performance on the original 10,000 MNIST dataset, the total number of learnable parameters, and then their performance when you do some alterations like shifting, rotation, or scaling. So what's pretty interesting here is that, if I were to like give like a summary or holistic summarization of like what's important in the good takeaways, convolution can increase the quality of features specific to image inputs. So this is seen comparing, this case, that is network 2, with this case, network 4. So the difference between these two is just going to be the fact that this one has a convolution operation. And you can see still that, performance has increased. It has actually increased quite substantially across the board. So this is because convolution operations take advantage of spatial relationships. Next is nonlinear activation. So nonlinear activation can add expressiveness to the model, increasing the performance with no increase in trainable parameters. So this is seen with this extreme jump from network 3 to network 4 when we add an activation layer. Next, pooling layers are great for downsampling while preserving network performance even on transformations. So for example, if we add a pooling layer here, we see increase in performance while substantial downsampling over here. and with not much like difference even on distortions to the test images. And so the total number of trainable parameters substantially decreases, and so training becomes much cheaper. And then if you stack convolution activation and pooling blocks together, it gives the best outcome for classifying input images, even when transformed while minimizing the number of learnable parameters. So this number of learnable parameters is extremely less compared to the rest, yet its performance is the best, along with, even if, inputs are distorted, it is still the best. Quiz time. Have you been paying attention? Let's quiz you to find out. The weights learned by two convolution layers in these two networks are the same. True or false? I'll give you a few seconds to answer this question. The correct answer is false, but can you tell me why? Give your reasoning in the comments below and let's have a discussion. And at this point, if you think I do deserve it, please do consider giving this video a like because it will help me out a lot. Now that's going to do it for quiz time, but before we go, let's generate a summary. Now, in summary, we've taken a look at 6 networks from no hidden layers to like an FC layer to a convolution layer, adding activation, pooling, and even stacking these layers, and observed their performance on the base MNIST test set. Then we also observed like the number of trainable parameters, and then also observe like what happens if we were to do some like shifting by 5 pixels, rotation by 30 degrees, or scaling by 0.5x, and observing the output on these models. And effectively wrote some conclusions about how convolution increases the quality of features specific to an image. Nonlinear activations add expressiveness to the model and can also like decrease underfitting. And then pooling is great for like downsampling while preserving network performance. And then stacking convolution activation and pooling blocks best gives outcomes for classifying images, even when transformed while minimizing the number of learnable parameters. And that's all that we have for today. I'm going to attach this notebook in the description below, so do check it out. And like I said before, if you like this video and I think I deserve it, please do consider giving this video a like because it will help me out a lot. Thank you so much for watching. Subscribe for more, and I will see you in the next one. Bye-bye.